Hello everyone, this is Dr. Bajigni. Nice to see you all. This is lecture 8. In this lecture I will cover chapter 6, series parallel circuits, or sometimes they call it combined circuit. As introduction to this chapter will cover circuits that combine series and parallel circuit, and also we will use Ohm's law along with both Kirchhoff's laws will be used. So again, because we already used Ohm's law with the series circuit and parallel circuit, so now since we have both circuits in one circuit combined, we will use the same thing as we used in those two circuits, Ohm's law and KVL and KCL. A series parallel circuit is a circuit that contains both series and parallel topologies. So again, from its name, so the name is series, which means there is a component or element, they will be considered series here. And so for example, R1 and R2, they are combined as R1 plus R2. And also R3 and R4 will be combined as R3 plus R4 because they are in series. Now, when we do when we combine and we try to find the equivalent resistance RT or R equivalent for this circuit, so always, so we cannot say that R5 is in parallel or in series with R3 because they are not sharing the same two nodes. Yes, they share this node, this is one node here, and as well as R6 also, they share with R5 and with R3 one node. But R5 and R6 are not sharing the second node of R3, and the same thing for R4. So R4, they're sharing the same node of R5 and R6, which is the bottom one, but they don't share the top one. So always when we do when we find the total resistance or the equivalent resistance of a series parallel circuit, we always look to the branches or elements that they are either in series, we combine them first. And after that, when we combine R3 and R4, we replace it with one resistor. So now this new resistor, which is the sum of R3 plus R4, this will be in parallel with the R5, and also in parallel with R6. And then after that, so then now we have this resistor, which is a combination of R3 and R4, in parallel with R5, in parallel with R6, we can use the formula 1 over R equivalent is equal to 1 over R equivalent is equal to 1 over R5 plus 1 over R6 plus 1 over the sum of R3 plus R4. After that, and then find R equivalent, we take the reciprocal of both sides, we determine R equivalent, then R equivalent will be added to R1 and R2. So now we have one complete or one circuit. It has one voltage source Vs and one resistance, we call it R equivalent. And then after that, we can find I by applying the Ohm's law, so I would be Vs over R equivalent. So again, we are going to use the same technique as we did when we find the R equivalent or R total for series circuit, and we do the same for same technique that we use when we determine R equivalent to find the R equivalent of a parallel circuit, and then we can combine, the final result. Okay, analysis of a series parallel circuit. Again, we will use whatever the information, whatever the formulas that we use, we use the combination of resistors in series, we will use the combination of resistors in parallel, we'll use a KVL and KCL and Ohm's law, and then we could use a voltage division principle, current division principle. We will demonstrate this in an example. So regarding what type of circuit we have, either a series circuit by itself or a parallel circuit by itself or combination of both, will be using the same techniques that we had. Okay, let's look to this example here. So this example, again, it's a combined circuit. Why? Because we have R2 and R3 are in parallel. Why? Because they share the same two nodes. And also, if there's a current coming in to the node, that current will split, will be divided into I2 and I3. So that's why we call it, so these two branches are in parallel, but with this one, it's in series. Okay, so let's see how to solve this one. So there is a kind of a rule of thumb that when we determine the equivalent resistance, when we have more than one resistors, so it is good to start at the far end away from the voltage source. So don't start with R1. Okay? Don't combine R1 with R2 or with R3 because they are not connected. R1 is not connected to R2 in series, as well as R1 and R3 are not connected in series, neither or nor in parallel. So the best way is always to start from this end here. So now we could see that R2 in parallel with R3, by the way, these two parallel lines, they represent this R2 and R3 are in parallel. So again, since we have two resistors in parallel, we could use the product over the sum formula, which is R2 times R3 over R2 plus R3. Okay, so we have, so this is the result here. 36 times 72 over 36 plus 72. So now we take off this, okay, we take this out, okay, these two, and replace it by one resistor, which is 24. So that resistance 24 will be connected in with R1 in series. So now we can find R equivalent will be 16 plus 26, 24. I think I recommend you guys to always, draw the new circuit. So after you determine, R2 and R3 in parallel, you replace these two. You see these 2 points here, these are here. Okay, so we take this out and put the equivalent. Okay, and then after that we can find I. Okay, whatever. So in this case we can apply the the KVL for this circuit here to determine I1 here. So I1 it is going to be distributed later on among the 36 ohm and the 72 ohm. Now to determine I1, again we apply KVL. So now since we have one loop, so always when we have one loop, we use KVL, apply KVL around the loop. So again, when we, okay, since we don't have the polarity assigned to the resistor, so always see the current flowing this direction. So always that the current goes from the higher potential. So this point will be a plus. and this point will be minus. Same thing, current going down, so always this point will be a plus and this point will be a minus. Always the current goes from a higher potential to a lower potential. So if, as a rule of thumb, any element such as a voltage, when the polarity are assigned, doesn't matter what the direction of the current, we cannot change these two polarity. We cannot change the minus and the plus, okay? But for those elements or those resistance that they are not assigned for the polarity, then according to our direction, so our direction going this way, which is I1 going this way, so then this polarity has to be a plus, this is a minus, this is a plus, this is a minus. Now we apply KVL as it said, so it will be, so since the arrow here, since the arrow of the current, since the arrow of the current is hitting the minus, so this is, will be a minus 20, and then the voltage across 16 will be a plus because the arrow, the current here is still hitting, first hitting the plus, so it will be a plus 16 times I, this is the volt drop across the resistance 16, plus the 24 again also, because the current again flowing in this direction, so it's going to hit the plus sign first, so it will be 24 times I1. That will be equal to 0, so we can combine the similar terms with 24 plus 16 is a 30, 24, so it will be 44, what's that here? 4, it will be 40. Let me erase this one, so it will be 40 I1 equals to 20. So we move the minus 20 to the other side, we change the minus, become a plus, and then we divide by 40 both sides, so it will be 20 over 40, will be 1/2 or 0.5 amps. Okay, now after that we go back to the original circuit. So now we have I1 is given, which is a 0.5 amps. So I1 is 0.5 amps. Okay, now according to the voltage divider, okay, we have a current coming in to the node. This is the node. And then we have I2 and I3 leaving the node. So this I1 is going to split into parts or two paths, the I2 and I3. So to find I2, when we apply the current divider rules or principle, we take the I1, which is the total current that entering the node, multiply by the opposite resistor's value, which is 72, over the total resistance of R2 plus R3, so it will be 36 plus 72. Okay, so I1 is 0.5 multiplied by 72 over, again, the sum. In this case, we have the, this is will be 8, and 7 plus 3 is 10. So this will be I2 will be 333.3 milliamps or 0.333 amps. Okay, same thing we can do for I1, for I3. So I3 would be, okay, will be IT, or the total current that entering the node, because always I1 is greater than I2 and greater than I3, or we know that if we apply KCL at this node, we have I1 coming into the node equals to I2 plus I3. Okay, so this is, we call it KCL. So KCL applied to the parallel branches and KVL applied to the loop. Okay, so the difference between KCL and KVL. So now if we go back to how to determine I3. So it will be I1 multiplied by, again, we multiply by the other resistor or the opposite resistor, which is R2, divide by the sum R1 plus R2 plus R3. So again, we are given the 0.5 as an I1, and R2 would be 36 over, again, the sum 36 plus 27. So the final answer will be 166.7 milliamps. Again, then, since we know the voltages and we can also find the voltage across the if we ask, for example, he doesn't ask the voltage across R2, but again, remember that Ohm's law. So always remember that Ohm's law is very important. And then the power formula are important formulas. Okay, so these are very important. So we have Ohm's law, power formulas, and also we have KVL and KCL. So these are the main rules or the main formula or the main theorem that we use to analyze the circuit. It doesn't matter whether it's a series circuit or a parallel circuit or a combined circuit. So always we use these rules. This rule KVL we use for a loop like this. KCL we use for a node when you have branches in parallel. Ohm's law, we can use it at any point, at any element, across this element, across this element, across this element, anywhere we can use, or across this element, across this element. Okay, so again, I'm just reminding you that you always think about KVL, KCL, Ohm's law, power formula. So now going back to find the, as I said, we could call this, let's say call this is V2 and this is V3. Okay, and this is an extra requirement. Okay, and so this is V3 again. So let me write it down. V3. Okay, so again, if we need to apply Ohm's law here, so it will be V2 is equal to I2 times R2. And we have I2, we already determined I2, it's 0.33 amps or 333.3 milliamps. So if we use this as an amp, so our voltage will be in terms of voltage. If we use milliamps, then my units for the voltage will be millivolts. So I2 is 0.333 multiplied by 36. And then you can use your calculator to find the value. Same thing for V3 will be I3 times 72. So again, when we apply Ohm's law, if we apply it across R3, we must use the current through the I3. We cannot use any other current. We cannot use I2. We cannot use I1. So since we are finding or determining or calculating the voltage across R3, you must use the resistance across that voltage and also the current passing through that resistance. Okay, so I3 is given or determined as 0.1667 multiplied by 72. Also, I could also find the voltage across the voltage here, V1. Also, V1 would be, what will be? Will be I1 times R1. Okay, so it will be I1 is 0.5 times R1 is 16. Again, when you apply Ohm's law, you have to ask yourself where I want to apply it, where, which element. You pick this element, the R1, then you need to find what is the current passing through the R1. What is the value of that resistance? You want to find the voltage across R2, you must know what is the current passing through R2 and what's the value passing through R2. Okay, so again, if I determine V1 and V2 and V3, then I have the option to use one of the formulas. So we know we could use V1, I1. Remember, see here, very important. If I need to find the power here, P1, the power here, P2, the power here, P3. Okay, it's P1, this has to go. V1, I1, because I call this as V1. Or I could use I1 squared times R1, okay? Or I could use V1 squared over R1, since I know V1. But if you decide to use I1, because you already had I1 before, you already determined I1, so, and then I2, so there's no need to use the other formula such as V1, I1 or V1 square root. But I'm just telling you that there is different way to determine the power absorbed by each resistor. And then again for P2 will be I2 squared R2. Okay, so when you apply also the formula of the power, you need to apply at a specific element. You have to use the information across that element. You cannot use a different information. So when we find P2, I should use I2. I shouldn't use I3 or I1. And I shouldn't use a different resistance than R2. And the same thing for the power absorbed by R3 will be I3 squared times R3. Remember here, subscript 3, subscript 3, subscript 3. Now, if I want to find what is the total power that will be delivered by the source. Now, there's two ways to find this. One way is that I apply the formula of the power at the 20 volt, at the supply. We know that the power that coming from the supply, it will be I, which is coming from the supply, and in this case is 1, times the voltage supply, which is the 20. So that will be 0.5 multiplied by 20, so it will be 10 watt. Or I could say PS, since the power delivered by the source must equal the power absorbed or consumed by the resistors, by the sum of the resistors. So it will be P1 plus P2 plus P3. So if you have those powers, you look down here, if you add this here, 4 plus 2, you get 10 watts, which is the same as this. So this one are same. So again, you have two options to determine the total power. So we have, it's one power, but that power that comes out from the source or delivered to delivered by the source must equal to the total power consumed by the elements or by the resistance. Okay, let me look to this practice problem 6.1. So for this circuit, find I1 and I2. So I need to find I1 and I2. Okay, now if I look to this circuit and calculate the power absorbed by each resistance. So we know that, okay, to find I1 and I2, I need to find I3 because I3 is going to loop around and come down here, okay? It's going to enter this node here. So we have a node here and a node here. Now, so for that I3 is going to enter this node here, for some reason, I couldn't mark this one here, but I put the node here, but actually it has to be on this, showing you here. See, here's the node here. Okay. So that's what's going to happen. Now, so in order to find I3, I want to combine these two resistors here. Okay, so it's going to delete what I wrote down here to, see it better. So now see these two nodes here and this node here. Okay, So these 40 and 60 sharing the same two nodes, and the I3 that coming into the node, to the left node, to this node here, if you saw that I'm pointing by the mouse here. So that means these two resistors, the 40 and 60 are in parallel. So then we have to calculate 40 in parallel with the 60. So again, we're using the product over the sum. Okay, so it will be 40 times 60 divided by 100. We have two zeros here, two zeros here. So it will be 24 ohms. So now I can redraw the circuit again. So this is called like simplify. I'm trying to simplify. I'm trying to replace these two resistors by one equivalent resistor, which is 24. So as a rule of thumb and as an advice to you guys, always try to reduce reduce the circuit, or simplify the circuit to a smaller one. Okay, so now this is a 24 ohms and this is 26. So now this is I3. Okay, now this is 100. So now I could use either the KVL around this loop here, or I could do more simplification and combine the 24 with the 26 and combine them in one resistor, and then apply Ohm's law to find I3. So this will be 26 plus, it will be 50. Okay, so 6 plus 4 and 2 plus 2 is 4 and 5. So now, you know, it's easy now. We apply Ohm's law. So then apply Ohm's law. So Ohm's law stated that, you know, need to find I3. So I3 will be the voltage V over R, so it will be 100 over 50, so it will be 2 amps. Okay, and this is what's the answer here. Okay, and after finding the current I3, then I could apply, then go back to the main circuit, which is this one here. So is I3 coming into the node, to this node here. So then to find I1, I use the, what I use again, I use the current division or current divider. Current divider said that to find I1, I will use I3 in this case, or IT, whatever the symbol we give it to our total current that produced by the 100 ohms, multiply by the opposite resistance. The opposite resistance is 60. Divide by the sum of the two resistors here. Okay, so the 26 is not involved with the I1 and I2. So the 6, which is 100, so that one will be, so we have 2 times 60 over 100. So this will be 120 over 100 will be 1.2 amps, which is the same as this answer. And then we do the same thing for I2. So I2 will be I3, which is 2 multiplied by the opposite resistor, which is 40. Opposite means the other resistor. Divide by 100, so it will be 0.8 amps, which is the same as this answer. Now, after that, we need to calculate the power across each resistor. Since we know I1, we know the resistance, so P1, the power dissipated by the 40 ohms, if we call this is a P1, and this is a P2, and this is a P3, whatever the name you give it, it's fine. Then it will be, or power of dissipated by the ohm, or we could call it P40 ohm, and this is P60, it doesn't matter what you give as a symbol, it's fine with me. Then we have P1 would be I squared. Now which I? I2? No. I3? No. Has to be I1 square. Multiply which resistance? 40. Okay, so I1 would be 1.2, I believe, if I don't forget, times 40. Okay, and then same thing for P2, it would be I3, no, I2 squared multiplied by 40, no, 60. Okay, and then P3, which is where's the P3? Here. What's the current we use? The current that goes through it, as we did for 60. Which current we use? I2. For the 40, which current we use? I1. So it will be I3 squared multiplied by 26. Okay, and if you do the calculation using your calculator, you should get those numbers also. Okay, now to look to this example here. Okay, now again, this example, it's a combined circuit as this one. I want to find R equivalent. What is the total resistance? If I want to replace the whole resistor, say by one resistance, what would be the value that equivalent to that? How many? 1, 2, 3, 4, 5, 6, 7 resistors. 1, 2, 3, 4, 5, 6, 7. Okay, so now where do we start? Is the question. It's very important. Where do we start? So again, do not start from this side here, where you have the arrow or they ask you to find the R equivalent, or sometimes you have the power supply connected to these 2 points. Do not start from here. Start from the other end, this here. Okay, and we know that 1 and 5, if I have a current flowing in the 1, the same current will flow in the 5, and also they are sharing one node, so that means these are connected in series. Okay, so we can combine that 2 here, 1. Now, we finish from this one, now we come down here. So 2 and 6, they are neither connected in parallel nor in series, because the current here is not the same as in current here, and also they are not sharing the 2 points, only share with 1 point. The other point of the 2 ohms is not shared with the 6 here, or neither shared with the 3. So that means I cannot combine the 2 and the 6. I cannot combine the 2 and 3 now. But I could combine the 6 and the 3 as in parallel, because they share the same 2 nodes. This is one node, it's one node, and then when there's a current here, this current will split. So the current has more than one path. So in this case, what we should do, should combine this one, so it will be 6 ohms, and this will be 3 in parallel with 6. So there will be 3 product over the sum. So we divide 3 by 3, 9 by 3 is 2, so it will be 2 ohms. So now I can redraw, and always when you do the, this called simplifying, you try to simplify this, try to reduce the circuit, make it smaller. So I'm reducing these 2 in one resistor here, so this will be 6 ohm, and then I reduce these 2 here into another resistors, which is, okay, so I'm writing down, this is 2 ohms, and this is 2 ohms, and this is 4. So I'm still trying to determine what is the R equivalent here. Okay, so now this circuit, this new circuit, this one here, is the same as this circuit, okay? I'm just trying to reduce. Now, if I look to this circuit, I cannot combine these 2 with this 6 here. Okay, I can't. Why I can't? Why I can't? I cannot combine, again, this circuit here, this 6 with the 2, because see this 6 here, it has 2 nodes here. So yes, it shares with the 2 with only one, okay? But the other end or the other point of the 2 is not shared with this, okay? So that's why these 2, the 6 and the 2 here, and this 6 also and the 2 here, they are neither in series nor in parallel. So what should I do now? I should now combine the, let me put back this line here. Now I could combine these 2 ohms with these 2 here because they are in series. So there's a current flowing in the top one, the same current will flow, and they are connected by 1 node. Okay, so now 2 and 2 is 4, and we have 6 here, 6 ohm. Now this will become, again, I'm going to draw this one. So this will be 6, and this will be 4, and this is a 4. Oh, sorry, I forgot to put the 8 here. So let's put the 8 down here and the 8 down here. And again, this is still, we call it R equivalent. So trying to find R equivalent. So let me erase what I had now and then redraw the circuit again. So it will be, again, will be 6 and 4 and 8 and 4. Okay, now if we look again, 4 and 8, they are not related. They are not in series nor in parallel. 4 and 6, same thing. 8 and 4 and 8 and 6. So what should I do now? These, if you look to these two here, they are related. They are connected in parallel. So now I can replace that resistance, and then I put the 8 here. So I take this out. See these 2 points here? These are the 2 points here. Okay, and then I finish the circuit, 4, 8, and I keep track of R equivalent so I don't forget where I'm trying to find my R equivalent. And so this will be the 4 times 6 over 4 plus 6. So the product over the sum. So the equivalent of this parallel resistors will be 4 times 6 over 10. So that will be 24 divided by 10, so will be 2.4. 2.4. Okay, so this will be 2.4. So that's okay. So that will be 4 and 2.4 and 8. So let me move to the next slide. So I don't want to. Okay. Okay. So this is what I am reaching. Okay. This is the. This is exactly the same as I had. Okay, so this is our final results here. So it will be, so basically R equivalent will be 4 plus 2.4 plus 8, which is this one. Okay, so again, if we go step by step, try to simplify the circuit and look to the branches, look to the elements. Look to the elements. If they are in series, combine them and add them. If they are in parallel, if they are 2, use the product over the sum. If they are more than 2, use 1 over R equivalent plus 1 over 1 plus 1 over 2. Okay, let's see this one here. Here we have, again, this is the practice problem. If we look again, do not start from here or from here, Start from the other end, from here. Far end, this is the far end. Far end, okay? So as you see here, these two are in series because the currents will be the same and they share 1 point. So there will be 4 plus 8, 4 plus 5. So it will be also this one. See this current here? So these 3 here are in series, okay? So it will be 9 plus 3 will be 12, okay? So then I can redraw the circuit here. Okay, so now this has become 12, and this is 4, and this is 3, and this is 6, 1, 2. And again, I'm not going to put the units here because, yeah, I mean, this is ohms again, so okay, I don't have enough space for that. Now, if you look to the 4 and the 12, they are in parallel because they share the same 2 nodes. And when the current entering this node is going to split. Okay, good. So now, which means that the 12 volt, the 12 ohms and the 4 ohms will be in parallel. So that means will be 4 times 12, 4 times 12 over 16. Okay, the product over the sum. So the 4 will cancel out. We have 4, 12 divided by 4 is 3 ohm. So that means these two will be replaced by 3 ohm resistor. Let me draw this circuit again. Okay, so this would be, okay, here's the 3 ohm. Here's the 3 ohm, which is coming from this one here, from this one. And we have the 6, and we have the 2, and we have the 1. See, every time we combine resistors, the circuit becomes smaller. So we shrink it, we reduce it. Okay. So now 3 and 3, they are in series, because if we assume a current here, so they share one node, the other two nodes, they are not shared, so they are not in parallel, they have to be in series because current is the same and they share only one node. So that means these two are in series, so we can replace this one by one resistor. So these 2 points here, which is this one here, this one. Okay, so these are the two nodes of the 6 now, they become a 6, and we have another 6 here. So this is a 6, and this is 3 plus 3 is a 6, and this is a 2, and this is a 1. So now this is in parallel. Why? They share two nodes, and if the current is coming in, this current will split. So now we have, so let me erase the top one here so we can have enough space to draw the new equivalent circuit. When you say equivalent, mean it's the same as the previous one. Okay. Now, now we have two resistors, the 6 and 6 in parallel. So we could use the product over the sum, or we could use the equal method. The equal method means I have two resistors are equal. So if I take value of one of them, divide how many, we have the 2, so it will be 2 ohms. So that means the 6 and the 6 will be equivalent to 3 ohms, and then we have the 1 ohm, and then we have the 2 ohms, and here's my R equivalent symbol. So now if you looking to this, all this complicated circuit, now we can make it even simpler. Now we can see that 2 and 3 and 1 are in series. So then it will be, the total resistance will be equivalent to 2 plus 3 plus 1. Okay, so 2 plus 3, so R equivalent is equal to 2 plus 3 plus 1 equal to 6 ohm, which is the same as with the answer of the book. Okay, so this is okay. I want you to do the example or follow the example again. Don't start from here, or start from here. So 1 and the 5, and then now remember that this point here, you can remove this node because this is one node, so you can remove this down here. You could draw this in here, either on this side. Okay, so this will be, you remove the 12 and put it here, okay, to make it simpler to visualize. Same thing, the 6 here, you can move it down here. So let me redraw this one. So the 6 ohm, you can move it down here, or in here, same thing, 6. And also the 12, you can move it down here. So the 12 and the 4 will be in parallel. The 1 and the 5 will be in series. And then the 6 and the 6 will be in parallel. So anyway, so start from this side and move backward, okay, until you reduce this complicated circuit to a simple one. Okay, let me. So this is the steps how to reduce the circuit. I want you to do this and follow. Okay, and for this one here, I'm going to show you how to solve this example here. We need to find I1 and I2 and I3 and I4. And since we have this one, so what you can do, you can combine, see these two here are in parallel, so 80 and 20, which is in this case is 16. And then you draw the circuit again. So every step you do, try to redraw the new circuit to visualize how the circuit will work and how to find this. So this is 40 milliamps, and we have an I1 here, and then we have, so this is will be I2, and this will be 16, and this will be the 14. So now the 16 and the 14, they are in series, so we can combine them in one resistor. So this will be 16 plus 14 is 30 ohms, and this is 70 ohms, and this is I2, and this is will be I1. So since you reach to this level here, you don't need to go further to reduce the circuit or simplify the circuit. Now you could apply the what we call it, the current divider. So we could apply the current divider by, here is this one here, to show you how to apply the current divider. What you could do here, okay, according to the rule of the current divider, we need I1 is equal to 40, which is the current entering the node, multiplied by the opposite resistor over the sum of the two resistors. Okay, and the same thing for determining I2 is equal to 40 multiplied by 30 over 100. Okay, now we're done with the I1. We found I2. Now we need to find I3. Okay, good. So now we know I1. So now I1 for I3 and I4 becomes like our total resistance that entering this node here. So now we can apply the current divider second time to find I3. So I3, it will be equal to I1, which is in this case, this is like this is our total current that entering this node. Okay, so we have total current entering this node, and then I1 will become a total current entering this node. So I1 multiplied by, since I'm looking for I3, so I multiply by 20, divide by 80 plus 20. And then the same thing for I4 will be I1, and again we already had an I1 and I2, so this is our I1, so it will be 28 multiplied by the opposite resistor, which is 80, divide by 80 plus 20, which is 100. So using your calculator, you will be able to determine the, now, if we want to find, find the voltage across each resistance, then we use Ohm's law. Okay, so what is the voltage across? What's Ohm's law? Ohm's says that voltage equal I times R. Very good. Now we need the voltage across V across the 14 ohms. Okay, good. The V across 14 ohms is the I1. What is the resistance? Is a 14. So I1 times 14. Okay, I need to find the voltage across the 80 ohm resistor. Good. So it will be I3 multiplied by 80. Remember, when we apply Ohm's law, okay, and I'm repeating this here because this is very, very important. When you need to find the voltage across any resistor, you must use the current that passes through that resistor and the value of that resistance. Okay, and that's what I'm doing here. Now, to find the, just say, let me say, if you have a space here to find the V across the 20 ohm resistor, it will be the current, which is I4 multiplied by the 20. Let me move this down here. So the voltage across the 20 ohm will be I4, which is, again, we had an I4 is 22.4 multiplied by 20. Okay, and again, remember this is a milliamp, so will be a millivolt, or you can convert it to a volt. Okay, so you have to pay attention to the units. So you have to multiply this 22.4 multiplied by 10 to the minus 3 to convert it into ampere or A. And then you do the same thing for the voltage across the 70 ohm resistor will be I2 multiplied by 70. It's not I1, it's not I3, it's not I4, it's I2. Okay, guys. Okay, again, determine the voltage drop across each resistor in this series power circuit. You have to find, first we need to combine these resistors first. So to do that, so this one is fine. So we can assume a current here is I1. This is a current here is I2. And we do the same thing as I3 is a current I4. Very similar to the previous example. Okay, so to find I2 in this branch here, so I have to combine that branch. Okay, and I have to combine the 12 and the 15, and also I have to combine the 6 and the 6. But if I look down here, the 12 and the 15, they are in series, so they'll be combined in one value, which is 27 ohm. And then the 6 and the 6, they are in parallel because they share the 2 points, and also the current is going to split. So I2 is coming in, it's going to split to I3 and I4. So that will be, now since it's an equal value, so it will be 6 over 2, will be 3 ohm. Or you could say 6 times 6 over 12. Same thing, the product over the sum, they give you the same answer as 3 ohms. Okay, now these two resistors are in series, so let's redraw the. Okay, so now we have 23 plus 3 is 30 ohm, and we have this is an I2, and this is an I1, and we have 50 here, we have 80 here, 80 milliamps. So again, the 80 is coming in, is going to divide by I1. So we have an I1 and I2, and then use the current divider. So if we use a current divider, will be I1 will be 80 multiplied by 30 over 80, and then I2 will be 80 multiplied by 50 over 80. So this will be I2. Now we go back to the original circuit here. Let me erase this one here. So now we have I2. Now I2, in this case, it becomes our total current entering this node here, or this node. So now we have to apply the same rules of the voltage divider to get I3. So I3 will be I2. So I2 was fraction of the total current. Now I2, it becomes our total current entering this node. So I2 multiplied by the 6, since both are 6, divided by 12, and then I4 will be again I2 multiplied by the other 6, divided by the sum, which is a 12. Okay, so this is how we solve this circuit here. Okay, so let me. So for this example, I'm going to skip it, and this will be the end of the chapter, and I will see you next time. And thank you everybody for your watching and for your listening.